Look up on a clear night, and the sky looks like pure chaos. Thousands of stars scattered across the dark at random. Watch it long enough, and the randomness dissolves. The same stars return to the same places. The moon keeps its schedule. The planets always come back around. The night sky is not a mess. It is one of the most orderly things you will ever look at. By the end of this video, you will understand why a universe this vast, this old, and this violent should settle into patterns at all, and why the answer is stranger than the patterns themselves. If you find these reflective explorations of the cosmos meaningful, a like or a subscribe helps us continue making them. To see how strange that order really is, it helps to notice that it does not stop at the sky. The same insistence on pattern runs through everything, on every scale, in places that have nothing to do with one another. A galaxy winds itself into a spiral. A planet wears its rings in flat, bright circles. Water freezes into a snowflake with 6 arms and never 5 or 7. A river, seen from above, splits and splits again into the same branching shape as the veins in a leaf and the veins in your own hand. Salt dries into cubes. Light moves in waves of perfectly even spacing. None of these things consulted the others. A snowflake has never met a galaxy. And yet the universe keeps arriving at the same small set of shapes, again and again, as though it has only a handful of ideas and an eternity in which to repeat them. And the repetition runs deeper than shapes. Every atom of gold in existence is identical to every other atom of gold, down to the last detail. Every atom of oxygen behaves exactly like every other, here, inside the sun, and in a galaxy whose light set out before the Earth had formed. The universe does not turn out slightly different versions of the same element. It stamps out perfect copies by the uncountable trillion, and has been doing so for as long as there have been atoms at all. This is pattern of the most exacting kind, a sameness so reliable that the whole of chemistry, and therefore the whole of life, is built on being able to count on it. What makes this more than a curiosity is that the patterns are not loose or approximate. They are precise enough to bet a life on. The planets do not merely tend to come back. They come back on a timetable so exact that we can say where Saturn will sit in the sky on a given night 1,000 years from now and be right to within a hair. A comet that visits once in a human lifetime can be told, decades ahead, the year and very nearly the day it will return, and it keeps the appointment. An eclipse can be predicted to the minute, centuries in advance, by people who will not live to see it. The universe does not just repeat itself, it repeats itself reliably, and that reliability is the thing that needs explaining. It is easy to miss how astonishing this is, precisely because it is so familiar. We grow up inside the order and stop seeing it, the way you stop hearing a sound that never changes. But the universe did not have to be this way. It is no trouble at all to imagine the alternative. A cosmos of pure noise, where nothing held its shape, where every region followed its own rules and abandoned them the next moment, where no arrangement of matter lasted long enough to be called a thing. That universe is perfectly easy to picture, and it would contain no stars, no planets, no chemistry, no living creatures, nothing that endured. Order, after all, is the rare case. There are vastly more ways for matter to be jumbled than arranged, more ways to be noise than signal, and left to chance. Jumble is what you would expect. Shuffle a deck, and you will almost never deal it back into its original order. The universe began shuffled, and somehow dealt itself stars, and galaxies, and the readers of this sentence. That we live in the patterned kind of cosmos, the kind where things last and recur and can be relied upon, is the first fact about it that demands an answer. For almost all of human history, the answer was design. The order had been put there on purpose. Something or someone had arranged the heavens the way a craftsman arranges the gears of a clock, set them turning, and stepped back. This is a natural thing to conclude, because in our ordinary experience, order really does come from a designer. A pattern in a fabric implies a weaver. A building implies an architect. A clock, above all, implies a clockmaker, and the sky, with its wheeling regularity, looked more like a clock than anything else people knew. To find such order and assume a hand behind it was not foolish. It was the obvious reading of the evidence. But the explanation that took shape over the last few centuries, assembled slowly by people staring through telescopes and scratching at equations, turned out to be stranger than design, and in its own way, more astonishing. No one arranged the stars. There was no hand, no blueprint, no plan being followed. And yet the universe is not random either. It sits in neither of the two places we instinctively reach for. It is neither chaos nor craftsmanship. The patterns are real and deep and everywhere, and they assembled themselves out of almost nothing, following rules that no one wrote down and no one enforces. It is one thing for a watchmaker to build a watch. It is another thing entirely for the parts to fall together into a working watch on their own, and then for that to happen everywhere, the same way, without exception. That is closer to what actually occurred. The order built itself. How something builds itself without a builder is the deep question here, and the answer comes together piece by piece. It rests, in the end, on a very small number of rules. Rules that never change from one place to the next or one moment to the next, and on what those unchanging rules quietly do when they are left alone for billions of years. To understand it, we will travel in two directions at once. We will go outward, from the sky over your head to the largest structures that exist, threads of galaxies stretching across distances the mind cannot hold. And we will go inward, beneath the visible motion, down to the laws themselves and the strange symmetry hidden inside them. And at every scale, large and small, near and unimaginably far, we will find the same answer waiting. That is where the journey ends. Where it begins is much closer to home, with the people who first noticed that the sky could be trusted. Long before there were telescopes or equations, before anyone could have told you what a star was or why it moved, human beings were watching the heavens and recording what they saw, not on paper, but in memory, in stone, in the slow accumulation of lifetimes. You can still find the marks they left. Stones set to catch the sunrise on a single morning of the year. Notches cut against a horizon where a particular star first returned. Passages built into tombs so that light would reach a chosen spot on a chosen day. These were not decorations. They were instruments, the first instruments, and they worked because the sky kept its appointments. Those watchers had no telescopes and no theories. They had only patience and the same sky we still stand under. They could not say why any of it happened, but they noticed, with a certainty that would shape everything that came after, that it happened the same way every time. And in that noticing, in that first quiet act of trusting the universe to repeat itself, the long human effort to understand the order of the cosmos began. Those watchers had a single instrument, and it was the sky itself. Without clocks or calendars, without writing in many cases, they learned to read time directly off the heavens, and they found 3 clocks running at once. The fastest was the sun, dividing light from dark, marking out the day. Slower was the moon, swelling and thinning through a cycle that returned every 29 or so days, marking the month, the very word a fossil of that monthly count. Slowest of all was the great wheel of the year, written in the changing height of the noon sun and in the constellations that traded places in the evening sky, rising a little earlier each night until, after 12 months, the whole pattern came round again. 3 rhythms nested one inside another, all of them perfectly dependable, all of them free for the price of looking up. This was not idle stargazing. For most of human history, reading the sky correctly was the difference between eating and starving. Plant too early and a late frost kills the seed. Plant too late and the crop never ripens before the cold returns. The sky was the only calendar accurate enough to get it right, and so people learned to tie the rhythms of survival to the rhythms overhead. In one ancient civilization, the most important event of the entire year, the flooding of the river that made its fields fertile, was announced by the sky in advance. A single brilliant star, absent from the heavens for weeks, would reappear low in the dawn just before the waters rose. The star did not cause the flood, but it kept the same appointment year after year, and a people who learned to watch for it could prepare for the most consequential event in their world before it arrived. The same wheel turned everywhere, and everywhere people learned to read it. The point on the horizon where the sun rose was not fixed. It crept north through the warming months and south through the cooling ones, pausing twice a year at the turning points we still call the solstices, then reversing. Mark that creeping sunrise against a far hill or a standing stone, and you had a working calendar built into the landscape itself, one that would tell you the season as reliably in 1,000 years as it did the day you set it down. The constellations did the same work after dark. A particular group of stars rising at sunset meant one time of year. The same stars rising at midnight meant another. The sky was a clock face the size of the world, and its hands never slipped. Some staked more than a harvest on it. Across the largest ocean on Earth, navigators crossed thousands of kilometers of open water, with no land in sight and no instrument but memory, steering by the points on the horizon where particular stars rose and set. They held in their heads a map of the turning sky, the order in which the stars climbed out of the sea, the paths they followed across it, the places they sank back down, and they trusted that map enough to set out from one tiny island toward another one they could not see, hundreds of kilometers away, certain it would be where the stars said it was. That is a staggering kind of confidence. It is the confidence that the universe will behave the same way out there, in the middle of an empty ocean, as it always has at home. None of this was the work of a single lifetime. A person watching the sky sees only a few decades of it, and the great cycles are slow. To pin down the wandering of the planets, or the gradual drift of the rising stars across the centuries, took generations of watchers handing their records down. Knowledge accumulated the way a reef is built, one patient layer at a time. And in several parts of the world, the earliest writing we have ever recovered is not poetry or law or trade, but astronomy. Lists of star risings, tables of the moon's phases, records of eclipses reaching back across hundreds of years. Before people wrote down their stories, they wrote down the sky. It was the thing most worth remembering, because it was the thing that could be relied upon and counted with. In all of this, those early watchers were doing something more profound than they could have known. They had not explained the sky. They had no real idea what a star was, or why the sun should climb and fall, or what kept the moon to its cycle. But they had discovered something that mattered more, for the moment, than any explanation. They had discovered prediction. They had learned that the universe could be trusted to do tomorrow what it had done today and yesterday, and for every remembered year before, not approximately. Exactly. The star would return on schedule. The sun would turn back at the solstice. The constellations would complete their wheel. You did not need to know why to know that it would, and to plan a life, a harvest, an ocean crossing, around the certainty that it would. To predict the sky was to hold a kind of power, and the people who could do it, the calendar keepers, the temple astronomers, the ones who guarded the records, often stood close to the center of their societies. Nothing demonstrated that power more dramatically than an eclipse. A sun that vanishes at midday is, to anyone unprepared, a terror without cause. But eclipses, too, return in long repeating cycles. And a watcher, with enough generations of records behind him, could see the rhythm and say before it happened that the darkness was coming, and that it would pass. To foretell the disappearance of the sun, and to be right, was as plain a proof as anyone could ask that the heavens, however strange, were not capricious. They were keeping a schedule, and the schedule could be read. That certainty is the quiet foundation everything else is built on. Every piece of science that came afterward, every law written down, every prediction confirmed, rests on the same assumption those watchers made first without ever stating it: that nature is consistent, that the rules do not change when no one is looking. It is the assumption a chemist makes in expecting a reaction to run the same way next week as it did today, and the assumption a physicist makes in trusting that a measurement taken here would hold on the far side of the galaxy. We tend to think of this as a modern and sophisticated idea. It is in fact the oldest idea we have, older than writing, and the ancient instinct behind it. The instinct to trust the repetition of the heavens was not superstition. It was correct. The universe really does remember itself. And yet, for all they got right, the watchers could go no further. They had the pattern, but not its cause. They could say with total confidence when the star would rise, and not the faintest thing about why it must. The deeper question, the one this whole journey is chasing, sat entirely beyond their reach. What makes the sky keep its appointments at all? What enforces the schedule? For most of human history, the question looked unanswerable, and one natural assumption made it harder still. It seemed obvious that the heavens were simply a different kind of place from the earth, a separate realm, perfect and changeless, running on rules of their own that had nothing to do with the messy, decaying world underfoot. Everything on the ground was born, decayed, and died. Iron rusted, wood rotted, flesh withered, whole kingdoms rose and fell. The heavens did none of this. The same stars our distant ancestors saw are the stars we still see. They do not age, do not fall, do not change. It was almost irresistible to conclude that they were made of something finer and ruled by something other than the corruptible world below. That assumption was the wall the explanation would have to break through. And when the answer finally began to come, centuries later, it started by erasing the line between heaven and earth altogether. With a single idea so simple, it is easy to underestimate. And so radical, it remade everything. That the heavens are not a separate realm at all. That the very same rules govern the falling of a stone from your hand and the wheeling of a star across the night, here and everywhere, without exception and without a break. The sky keeps its appointments for the same reason a dropped stone always falls. And understanding that one reason is where the answer to the whole mystery truly begins. The idea that broke the wall came from watching something fall, an apple by the old story, or simply the ordinary fact that things drop when released. And the question that turned it into a revolution was whether the same pull that brings an apple to the ground might reach further than anyone had supposed. Further than the treetops, further than the clouds. Far enough, in fact, to reach the moon. Isaac Newton's radical step, late in the 17th century, was to propose that the moon is also falling, perpetually, exactly as the apple falls, and that the only reason it never lands is that it is moving sideways so fast that it keeps missing the earth as it falls toward it. The curve of its fall and the curve of the Earth's surface match, and so the moon circles, forever falling and forever overshooting, held by the very same force that empties an apple from a branch. This was an act of demolition, disguised as a piece of arithmetic. For thousands of years, the heavens had been a realm apart, governed by their own perfect rules, untouchable by anything as lowly as the physics of falling stones. Newton erased that boundary in a single stroke. The force that governs the orchard governs the moon, and it does so by one rule he could write as a single equation. An equation that gave not just a story, but numbers, predicting where a planet would be with an accuracy that left no room for doubt. The same law, written once, applied in both places. The wheeling of the heavens was no longer a separate mystery requiring a separate explanation. It was the same ordinary physics we feel every time we drop something, simply carried out on an enormous stage. The order in the sky and the order on the ground were revealed to be one order. But Newton's unification, for all its power, reached only as far as the solar system. It explained the moon, the planets, the comets. It said nothing directly about whether the same rules held in the depths of space, around other stars, in other galaxies, across the unimaginable gulfs that separate them. And here the problem seems, at first, completely hopeless. You cannot visit a distant star. You cannot carry a laboratory to another galaxy and check whether physics behaves itself when it gets there. The objects we most want to test are precisely the ones we can never reach. So firmly did this seem to be a permanent limit on knowledge that one prominent thinker, early in the 19th century, chose the chemical composition of the stars as his example of something humanity would never, ever know. The stars were the very definition of the forever unknowable. He could not have chosen a worse example, because within a few decades, the answer was pouring in. It comes to us, it turns out, on a beam of light. The key was the discovery that light carries, written into it, a precise record of what produced it. Heat any element until it glows, spread its light out into a spectrum, and you do not get a smooth smear of color. You get a set of sharp, bright lines at exact positions, and the arrangement of those lines is unique to that element, as distinctive as a fingerprint, set by the unchanging internal structure of the atom itself. Hydrogen has its pattern, helium has another. Iron has a dense thicket of lines all its own. No two elements share a fingerprint, and each one's is fixed, the same every time. And a spectrum carries more than composition. Folded into the same light are the temperature of the source, its motion toward us or away, even the magnetism threading through it. A single beam of starlight is a dense and detailed message, and we have learned to read it. The same fingerprints work in reverse. An element does not only emit its private set of lines when it glows, it also absorbs at exactly those positions when light passes through it, stamping a matching set of dark gaps into the spectrum beyond. This is how we read the makeup of a cool cloud of gas silhouetted against a brighter source behind it, and how the sun's own outer layers print their signature onto the sunlight streaming past them. Whether the message is written in bright lines or dark ones, it says the same thing, and it always agrees with itself. This means that the light from anything, anywhere, is a report on its own nature. Point an instrument at a star hundreds of light years away, spread its light into a spectrum, and the fingerprints are there. The lines of hydrogen, of helium, of calcium, and iron etched into the starlight. We saw earlier that every atom of an element is identical to every other. This is how we know that sameness is not merely a fact about the atoms here, but a fact about the entire universe. Because when we read those distant fingerprints, they match. The hydrogen lines in the light of a star on the far side of the galaxy fall in exactly the same places as the hydrogen lines we produce in a laboratory on a Tuesday afternoon. Not roughly the same places in the same proportions, with the same spacing. The hydrogen out there is the same hydrogen, obeying the same rules, as the hydrogen down here. There is a striking proof of how powerful this reading became. One element was found in the sky before it was ever found on the ground. A set of spectral lines appeared in the light of the sun that matched nothing known on Earth, and rather than dismiss them, astronomers concluded they belonged to a new element, one not yet discovered in any laboratory. They named it after the Greek word for the sun, helium. Only decades later was helium finally isolated here on Earth, confirming what the sunlight had already announced. Think about what that means. We identified a substance we had never touched, never held, never seen, on a body 150 million kilometers away, purely by reading its signature in light. The universe had handed us a sealed message, and we opened it correctly. And when we finally checked, the message was true. We have even put the deeper rules themselves on trial. The exact spacing of those lines depends on the fundamental strengths built into physics, the numbers that fix how firmly an atom grips its electrons. If those numbers had drifted even slightly across billions of years, the ancient fingerprints would sit a little out of step with fresh ones made today. Astronomers have gone looking for exactly that, comparing lines in light from the deep past against the same lines produced in the laboratory now, and within the finest precision they can reach, nothing has moved. The constants of nature appear to be exactly that. Constant, not only across all of space but across nearly all of time. Push the instrument to its limit, and the conclusion only hardens. We can read the fingerprints in light from galaxies billions of light years away. Light that left its source before the Earth had formed, before the Sun had formed, when the universe itself was a fraction of its present age. That light has crossed almost the entire history of the cosmos to reach us, and it still carries the same lines, the same elements, the same laws. Often the whole pattern is stretched, shifted bodily toward the red end of the spectrum by the expansion of the universe across the eons of its travel. But the fingerprint survives the stretching. The spacing gives it away. Hydrogen, stretched, is still unmistakably hydrogen. Everywhere we have ever looked, in every direction and at every distance, across space and deep into the past, the rules are the same rules. Physics does not have a local edition. And that, finally, is the bedrock the whole mystery stands on. Hold on to what it means. If the rules of the universe changed from one place to another, or drifted from one age to the next, nothing could ever repeat. Each region of space would be its own private chaos, running on laws that applied nowhere else and lasted no longer than the moment. There could be no patterns, because a pattern is nothing more than the same thing happening again. And the same thing can only happen again if the rules that produce it stay put. But the rules do stay put. They are identical everywhere, unchanged across the whole life of the cosmos. And so the same causes produce the same effects. Not occasionally, not approximately, but always and everywhere. Drop a stone here, drop a stone in another galaxy, and it falls the same way. Form a star here, form a star 10 billion light years away, and it forms by the same steps into the same kind of object. A pattern at its root is simply the universe being consistent with itself, and we have now seen that it is consistent with itself all the way out, to the edge of what we can observe, and all the way back to nearly the beginning of time. This is the deepest reason the night sky keeps its appointments, and the watchers were right to trust it. But consistency, by itself, only opens the door. It tells us that patterns are possible, that the universe will not erase its own work from one moment to the next. It does not yet tell us why there should be galaxies, rather than an even haze, why matter should gather into anything at all. Lawful consistency is the stage. Something still has to act upon it, to take a young universe of almost perfect smoothness and sculpt it, over billions of years, into stars and galaxies, and the vast architecture that strings them together. Of all the unchanging rules we have just found written everywhere, one above all others does that building. It is the quietest force we know, and the weakest, and given enough time, it is the most powerful sculptor in existence. The force is gravity, and the first surprising thing about it is how astonishingly weak it is. We do not usually think of gravity as weak, because we spend our lives pinned to a planet by it. But the planet is the trick. It takes the entire mass of the Earth, every rock and ocean and cubic mile of molten core, 6,000 billion tons of it, to hold you to the ground with the modest force you feel in your legs, and you overcome it constantly. Every time you stand up, you defy the gravity of the whole planet with a small flex of muscle. A child's magnet, no bigger than a coin, can pluck a paperclip off a table. And in that instant, the magnetism of a sliver of metal beats the gravitational pull of the entire Earth, working in the opposite direction. Measured against the other forces of nature, gravity barely registers. The electric force between two protons is stronger than the gravity between them by a factor so large it has some 36 zeros in it, a number with no useful name. It helps to know the company gravity keeps. Nature runs on 4 fundamental forces, and gravity is the runt of the litter. 2 of the 4 work only inside the atomic nucleus, a strong force that glues the nucleus together and a weak force behind certain kinds of radioactive decay. Both of them powerful, but with a reach so short they have no say over anything larger than an atom. The third is electromagnetism, the force behind light, chemistry, magnets, and very nearly everything you touch or feel in daily life. And then, last and least, by an almost comical margin, comes gravity. On the scale of 2 particles, it is nothing, a rounding error beneath a rounding error. So here is the puzzle. The weakest force in nature, by a margin almost too large to write down, is also the force that shapes the largest things in existence, that gathers stars and flings galaxies into their orbits and builds structures spanning hundreds of millions of light years. How does the feeblest player end up running the whole game? The answer lies in 2 properties that gravity alone possesses. The first is that gravity is universal. It acts on everything. Anything that has mass, anything that carries energy, feels it and exerts it, with no exceptions and no escape. There is no substance immune to gravity, no material you could build a shield from, no way to be neutral toward it. Every particle in the cosmos pulls on every other particle across any distance all the time. The other forces are far more selective. The nuclear forces act only on certain kinds of particle and ignore the rest. The electric force acts only on things that carry charge, and a great deal of the universe carries none. Gravity grants no exemptions. It is the one force that touches literally everything there is. The second property is the decisive one, and it is easy to state. Gravity only ever attracts. It never pushes. There is no such thing as anti-gravity, no negative mass that repels, no way to make 2 lumps of matter fly apart by gravity alone. Every scrap of matter pulls every other scrap closer, and that is the only thing gravity ever does. This one-sidedness is genuinely strange, and physicists have probed it. They have wondered whether antimatter, the mirror image of ordinary matter, might somehow fall upward, repelled where ordinary matter is drawn. And recently they put antimatter in a tall column and watched. It fell. Antimatter drops, just like everything else. As far as anyone has ever been able to find, gravity has exactly one direction, inward, and no opposite at all. To see why that single sign matters so much, compare gravity with the electric force, which is far stronger. Electric charge comes in 2 kinds, positive and negative. Like charges repel, opposites attract, and the consequence of having 2 kinds is that they cancel. Ordinary matter contains almost exactly equal amounts of positive and negative charge, balanced so finely that, seen from any distance, it appears electrically neutral. Pile up a mountain, a planet, a star, and the colossal electric forces of all those charged particles very nearly perfectly cancel, leaving almost nothing felt from outside. Gravity cannot cancel, because it has only one sign. There is no negative mass to balance the positive, no repulsion to offset the attraction. And so where the electric force, for all its strength, neutralizes itself and fades into the background as objects grow larger, gravity does the opposite. It accumulates. Every additional particle adds its pull to the total, and nothing ever subtracts. Double the matter, and you exactly double the reach. There is no ceiling, no point at which it saturates or turns back on itself. Gravity is feeble between two small things, but it is relentlessly additive, and addition, carried on long enough, beats anything. Put those two properties together, and the consequence is inevitable. Gravity touches everything, and gravity only adds. So as you consider larger and larger collections of matter, the forces that cancel themselves drop away, one by one, until only gravity is left standing. The nuclear forces vanish almost at once, confined to the nucleus and blind to anything bigger. The electric force reaches across any distance, like gravity, but cancels itself into silence on any large scale. That leaves a single force with both infinite reach and no cancellation. One lonely candidate to govern the architecture of planets, stars, galaxies, and everything beyond. On the largest stages in the universe, gravity is not merely the strongest influence. It is very nearly the only one. And the ladder it climbs is staggering. The same single force that holds you to the ground holds the moon to the earth, and the earth to the sun across 150 million kilometers, and the sun to the galaxy across tens of thousands of light years, and whole galaxies to one another across millions of light years of all but empty space. One rule, unchanged, reaching from the fall of a dropped cup to the binding of structures so vast that light needs millions of years to cross them. Nothing else in nature spans that range. Gravity does it without effort, because spanning that range is simply what an attractive force of unlimited reach does. It is the same equation Newton wrote for the apple, quietly doing all of it. This is why gravity is the great organizer, and it organizes through a quality we might call patience. It does not work quickly. The pull between two distant clouds of gas is almost nothing. The motions it produces are slow beyond human reckoning. But gravity never rests and never reverses. It does not tire, does not pause, does not change its mind. It applies the same gentle inward tug, everywhere, in every direction, for as long as the universe exists, and the universe has given it nearly 14 billion years to work. A force that only ever draws matter together, that acts on everything, that reaches across any gulf, and that has all the time in the world, will do one thing above all others, given that time. It will gather. Scattered matter will be drawn into clumps. Clumps will be drawn into larger clumps. Smoothness will give way to structure. Look at it this way. The universe began as very nearly a uniform mist of gas, and gravity has spent its entire history sorting that mist into lumps. Every star is a lump gravity made, and once made, it is held in shape by that same pull. At every instant, gravity is trying to crush the sun smaller, and only the outward push of its nuclear fire keeps the squeeze at bay. A star is a standing truce between gravity pulling in and heat pushing out, and that truce is what holds it together for billions of years. Every planet, every moon, every galaxy, and every creature standing on any of them is matter that gravity gathered out of the haze. This is also where gravity begins to answer our real question. Because the same force acts the same way everywhere, it does not only make structure, it makes the same kinds of structure over and over. Wherever enough matter gathers, gravity pulls it into a ball, which is why stars and planets are round and not some other shape. Wherever that gathering matter is also turning, gravity flattens it into a disk. The repertoire is small, and it repeats, here and in a galaxy whose light is older than the Earth, because the rule behind it is one rule, applied without variation. Gravity does not just build structure, it builds the same structures again and again, and that repetition is the first place our pattern truly begins to come from. And yet there is a piece still missing, because patience and attraction alone are not quite enough to explain what we actually see. If the early universe had been perfectly smooth, matter spread with flawless evenness in every direction, then gravity would have had nothing to grip. Every point would have been pulled equally in all directions at once, the tugs canceling perfectly, and the smoothness could in principle have persisted, an unbroken haze pulled everywhere and therefore going nowhere. To build galaxies, gravity needs a flaw to work on. It needs the early universe to have been not quite smooth, to have carried some faint unevenness, some region a little denser than the rest for the pull to favor. And it needs a way to take that faint head start and run with it, to turn the slightest difference into the deepest structure. There is such a way. It is a kind of runaway, a feedback in which the rich grow inevitably richer, and it is the mechanism that turned a whisper of unevenness in the infant cosmos into every galaxy that hangs in the sky tonight. The runaway has a simple logic, and once you see it, you see why structure was all but inevitable. Picture the early universe as a vast sea of gas, almost perfectly uniform, filling all of space, but carrying the faintest ripples of density. Here a region a hair denser than average, there a region a hair thinner. Now fix your attention on one of the slightly denser patches. Because it holds a little more matter than its surroundings, it has a little more gravity, and so it pulls on the gas around it slightly harder than average, drawing a little extra material inward from the thinner regions nearby. But the moment it does, it contains still more matter and therefore still more gravity, and so it pulls harder again and gathers more. Every bit of matter it draws in strengthens the pull that will draw in the next. The denser it becomes, the faster it grows denser. That is the runaway, and it has only one direction. This kind of feedback, where a change feeds upon itself and amplifies, is what physicists call an instability. And it is worth being clear about how different it is from the way most things behave. The great majority of nature's arrangements are stable. Nudge them, and they return. A marble in the bottom of a bowl, pushed to one side, simply rolls back to the center. But balance that same marble on top of an upturned bowl, and the situation reverses. The slightest touch sends it rolling away, and the further it rolls, the steeper the slope it meets, so it rolls faster and faster still. A nearly uniform universe filled with gravitating matter is like the marble on the dome, not the marble in the bowl. The evenness looks calm, even placid. It is, in fact, precarious. Any departure from perfect smoothness, however small, does not heal. It grows. That growth is not instant, because gravity does not get to work unopposed. Two things push back against the gathering. The first is heat. The early universe was ferociously hot, and hot gas has pressure. It pushes outward, resisting any attempt to squeeze it, exactly as the air in a pump shoves back when you press the handle. The second is the expansion of the universe itself. Space was stretching in every direction, carrying matter apart, working in direct opposition to gravity's effort to pull it together. For a long stretch of early history, the formation of structure was a tug of war, gravity hauling inward, pressure and expansion dragging outward, with the outcome hanging in the balance. Only in the regions that had begun with enough of an excess could gravity slowly, narrowly win, pulling matter together faster than the expansion could thin it out, and the pressure could resist it. This tug of war set a kind of entry fee. A clump too small could not win. Its feeble gravity was no match for the pressure trying to puff it back out, and it simply bounced, dissolving back into the general haze. Only a region above a certain size, holding enough matter for its gravity to overpower the push, could cross the line and begin to fall together for good. So the universe did not collapse everywhere at once. It collapsed selectively, in the places that were both dense enough and large enough to win, and left the rest behind. But once a region wins that contest, the runaway takes over without mercy. What began as a patch a minuscule fraction denser than its neighbors becomes, across millions and then billions of years, dramatically denser, a slowly collapsing cloud, then a tightening knot, then a gravitationally bound object that holds itself together even as the rest of the universe flies apart around it. And as it draws matter in, the regions it draws from grow thinner, surrendering their gas to the greedy center, so that the empty spaces empty further. The contrast sharpens at both ends at once. Gravity widens every gap it is handed. The dense grow denser, the void grows emptier, and a cosmos that began very nearly featureless sorts itself, by this single mechanism, into somethings and nothings. And it built from the bottom upward. The first regions to win the contest were relatively small, and they collapsed first. Then these early clumps, now dense knots of matter in their own right, pulled on one another and gathered into larger groupings, which gathered into larger ones still. Structure grew the way a snowball grows, small pieces packing into bigger pieces over time, the runaway working at every scale at once. Countless tiny victories of gravity over smoothness compounded, across the eons, into the grandest architecture there is. The scale of the amplification is genuinely staggering, and it is the heart of why this matters. The seeds were fantastically slight. The early universe was smooth to a degree almost beyond imagining, the densest regions barely denser than the thinnest. A difference so small, you could have stared at it forever and seen nothing but uniformity. And yet from that barely there unevenness, gravity built galaxies, which are regions millions upon millions of times denser than the average of the cosmos. The runaway took a difference too faint to perceive and magnified it, over the long patience of cosmic time, into the difference between a blazing star and the empty dark between the stars. It is an amplifier of colossal gain, and structure is what its output looks like. There is an everyday cousin of this runaway, and it is the way money grows at compound interest. A sum left alone earns a little, then earns on its earnings, and then on those earnings again, so that what starts as a trickle becomes, given enough time, a flood. The growth feeds the growth. Gravity does exactly the same with matter. A clump's pull earns it more matter, which earns it more pull, which earns it more matter, compounding without pause for billions of years. It is no wonder the final sums are so enormous. Sit with one consequence of this, because it is close to astonishing. The map of the universe today, where the galaxies hang, where the great clusters gather, where the enormous empty voids yawn between them, is, in a real and literal sense, a magnified picture of where the infant universe happened to be very slightly denser and very slightly thinner. The structure that fills the sky is the grown-up form of the newborn cosmos's tiny imperfections. Every galaxy marks a spot where, in the first moments of everything, there chanced to be just a little extra. The universe did not have its structure imposed on it from outside, by any hand. It unfolded that structure from a pattern already faintly present within it, present from almost the very first instant, and then it spent 14 billion years developing the photograph. The amount of that original unevenness mattered, too, more than almost anything else about the early universe. Had the cosmos been born perfectly, flawlessly smooth, with no seeds at all, gravity would have had nothing whatever to grip. The haze would have thinned forever as space expanded, and not a single star would ever have lit. Had it been born too lumpy, the runaway would have run too hard and too fast, slamming vast regions together into black holes, long before stars or galaxies could take shape. The universe we actually live in began with seeds of just the right faintness, small enough to take billions of years to grow, large enough to grow at all. That narrow setting, whatever fixed it, laid the foundation for every structure that would ever exist, including the one reading these words. It is worth being clear about what this mechanism does not require. It needs no plan, no guiding hand, no blueprint specifying where each galaxy should sit. It needs only two things: a force that always attracts, which we have, and a starting field of faint imperfections for that force to amplify. Give gravity those two ingredients, and structure is not a lucky outcome, but a forced one, The order assembles itself, not in spite of the early universe's flaws, but because of them. The imperfections were never blemishes on the smoothness. They were the seeds of everything. All of which leads to an obvious and rather uncomfortable question. This is a beautiful mechanism, but it rests entirely on a single assumption: that the early universe truly did carry those faint seeds of unevenness. Are we simply inventing them because the explanation demands them? It would be a fair challenge, and a damning one, were it not for one extraordinary fact. We do not have to assume the seeds. We can see them. There exists something astonishingly close to a photograph of the universe, as it was long before any star had formed, an image of the cosmos in its infancy, a few 100,000 years after the beginning, and the seeds are right there in it. Faint mottlings of slightly more and slightly less, sitting exactly where the runaway would later raise the galaxies. That image is the oldest light there is. It has been traveling toward us for almost the entire age of the universe, and the story of how we stumbled upon it, by accident, while trying to get rid of an annoying hiss, is one of the strangest in all of science. Start with the strange gift that light takes time to travel. Because its speed is finite, fast but not infinite, to look out into space is always to look back into the past. The sun you see is the sun of 8 minutes ago. A star 1,000 light years away you see as it was 1,000 years ago. And the further out you look, the younger the universe you are seeing, until, if you could look far enough, you would be looking all the way back toward the beginning. There is, it turns out, a limit to how far back you can see, a wall beyond which no light reaches us, and that wall is not empty. The wall itself is the photograph. For its first few 100,000 years, the universe was too hot to be seen through. Everything was crushed together and blazing, so hot that atoms could not hold together at all. Electrons were torn loose from their nuclei and roamed free. And a fog of free electrons is opaque to light, because a particle of light cannot travel far through it before colliding with an electron and being knocked off course. The whole universe glowed like the inside of a star, a brilliant, featureless fog, and light could not move through it in a straight line. Had you somehow been there to look, you could not have seen across a room, because the room itself was made of light endlessly scattering off itself, going nowhere. Then, as the universe expanded, it cooled, and at an age of about 380,000 years, it crossed a threshold. It became cool enough, at last, for electrons to settle onto nuclei and stay bound there, forming the first stable atoms, most of them simple hydrogen. And in the moment the free electrons were swept up into atoms, the fog lifted. Light, no longer endlessly scattering, was suddenly free to travel in a straight line across the cosmos. The universe turned transparent in a single great change, very nearly everywhere at once. The light that was set loose in that moment is still flying through space today. It has been traveling unimpeded for nearly 14 billion years, and a little of it is reaching you as you watch this. That ancient light has not had a restful journey. The universe it crosses has been expanding the entire time, stretching the very space the light moves through, and stretching the light along with it. What began as a fierce glow, once as hot as the surface of a star, has had its waves drawn out longer and longer, sliding down from visible light through the infrared and into microwaves, cooling as it stretched until it now carries a temperature of just under 3 degrees above absolute zero, the faintest imaginable warmth against the deep cold of space. It arrives from every direction at once, a whisper of microwaves filling the whole of the sky. We call it the cosmic microwave background, and it is the oldest light there is, the afterglow of the hot young universe, still washing over us from the edge of the observable past. You have almost certainly met it yourself, without knowing. On an old analog television tuned to no station, a small part of the snowstorm of static fizzing across the screen was this very radiation, the afterglow of the early universe, caught by the aerial along with everything else. A faint fraction of that meaningless noise was the oldest light in existence, arriving in your living room from the dawn of time. We found it by accident, and the story is very nearly comic. In 1965, two researchers at a laboratory in New Jersey, Arno Penzias and Robert Wilson, were working with a large horn-shaped antenna, trying to make careful radio measurements of the sky. They were plagued by a persistent hiss, a faint background static that came from every direction they pointed the instrument and simply would not go away. They checked everything. They ruled out interference from the nearby city, from their electronics, from the wiring. They discovered that a pair of pigeons had been roosting inside the antenna and coating it with droppings, and they evicted the birds and cleaned out the mess, and still the hiss remained. Exactly the same from every patch of sky, by day and by night, through every season of the year. What they did not know was that, only a short distance away, another group of physicists had been working out that the universe, if it had truly begun in a hot, dense state, ought to be filled with precisely such a radiation, a faint afterglow surviving from the era when the cosmos cleared, cooled by the long ages into microwaves. That group had even begun building an instrument to go looking for it. When the two teams were finally put in touch, the meaning of the hiss became clear in a single conversation. Penzias and Wilson had not found a flaw in their antenna. They had found the afterglow of the early universe. They had been listening, without realizing it, to the light set free when the cosmic fog first lifted, the oldest signal in existence, and they had very nearly dismissed it as noise. It would earn them, some years later, the Nobel Prize. And it turned the hot early universe from a bold speculation into something we could observe directly, lying open across the whole sky. It did something larger still. For years there had been a real contest between two pictures of the cosmos. One in which it had a hot, dense beginning and has expanded and cooled ever since, and one in which it had always looked much as it does now, with no special beginning at all. The afterglow decided the argument. A universe that had always been roughly as it is should carry no such relic glow. A universe born hot and dense must. The hiss in the antenna was the fingerprint of a beginning. And once it was understood, the hot early universe was no longer one idea among several. It was the one the evidence demanded. It is worth pausing to grasp what the cosmic microwave background actually is. It is a snapshot of the universe at one particular moment, the moment it became transparent, frozen in that instant and delivered to us across 14 billion years of travel. Every patch of that microwave sky is a view of the infant cosmos as it was when it was only a few 100,000 years old, long before the first star kindled, before any galaxy existed, before the runaway had built a single thing. It is quite literally a baby picture of the universe, the earliest image it is physically possible to capture, because there is no older light to find. Behind it lies only the fog, and the fog cannot be seen through. And the first thing this picture tells us is how astonishingly smooth the early universe was. The microwave glow is very nearly the same temperature in every direction you look, across the entire sky, matching from one side of the heavens to the other to about 1 part in 100,000. Picture a landscape so level that the height of its tallest mountain above its deepest valley amounted to less than the width of a hair, and you would have something like the evenness of the infant cosmos. This is the smoothness we kept invoking, the near-perfect uniformity that gravity required as its starting canvas. And here it is, not assumed but measured directly, written plainly across the oldest light in the universe. But only very nearly the same. When the temperature is measured with enough precision, the smoothness turns out not to be perfect. There are ripples in it, regions very slightly warmer and very slightly cooler than the average, departing from it by that same tiny fraction, 1 part in 100,000. Detecting them at all demanded instruments of extraordinary delicacy, lifted above the distorting blanket of the atmosphere on satellites built for the single purpose of mapping the microwave sky. The first of these, in the early 1990s, revealed the ripples for the very first time, and later missions sharpened the map until every faint modeling stood out in fine detail. And those ripples are the seeds. The slightly warmer, slightly denser spots scattered through that ancient light are the very unevenness the explanation needed all along, the faint head start that gravity's runaway would later seize and magnify. We are looking, in the cosmic microwave background, at the original pattern, the blueprint of all cosmic structure, caught and held in the instant before gravity began to draw it out. And here the whole argument closes into a circle, and the circle holds. Take the exact pattern of ripples measured in that ancient light, the precise map of where the early universe was a touch denser and a touch thinner. Feed it into a computer as the starting condition. Then instruct the simulation to do nothing but apply gravity, the same runaway we have followed, and let it run forward across billions of years of cosmic time. What emerges on the screen is a universe. Not a vague resemblance to ours, but a detailed match. The same kind of vast web of structure. The same filaments and clusters and great empty voids. The same statistical scattering of galaxies that astronomers find when they survey the real sky. The seeds in the ancient photograph grow, under nothing but gravity, into the cosmos we actually inhabit. The prediction the runaway makes, beginning from the seeds we can see with our own instruments, matches the universe we live in. This is about as close as cosmology comes to a finished sentence. We can see the seeds in the oldest light that exists. We understand the mechanism, gravity's patient runaway, that amplifies them. And when we run that mechanism forward from those very seeds, it builds a universe like ours. The structure of the cosmos is not assumed, and it is not imposed from outside. It is grown by a force we understand, from a pattern we can photograph. The order assembled itself out of the faint imperfections of the dawn, and we are holding the baby picture that proves it. Which leaves one last thing to look at directly, not the seeds and not the mechanism, but the finished work. When gravity finishes amplifying those ripples across billions of years, what exactly does it build? What is the largest structure in the universe, the grandest pattern the runaway raises out of the faint unevenness of the beginning? It has a definite shape, and that shape is among the strangest and most beautiful things in all of science. The answer is the largest pattern there is, and for most of human history, no one suspected it existed. Until only a few decades ago, you might reasonably have guessed that galaxies were sprinkled more or less evenly through space, the way stars seem sprinkled across the night sky, or else scattered at random with no arrangement at all. They are neither. When we finally managed to map where the galaxies truly sit, not on the flat sky but in 3 dimensions, at their real distances, we found them arranged into a single colossal structure that stretches across the entire observable universe, and it looks like nothing anyone had pictured. It looks like a web. The galaxies are strung together into long, bright filaments, threads made of thousands upon thousands of galaxies, reaching across hundreds of millions of light years. Where several of these filaments run into one another, they pile up into dense knots, and those knots are the great clusters of galaxies, the richest, most crowded concentrations of matter in the cosmos. And between the threads lie the voids, enormous, almost perfectly empty bubbles of space, tens and even hundreds of millions of light years across, containing very nearly nothing at all. The matter of the universe clings to the walls and edges of these bubbles and leaves their interiors hollow, so that the whole arrangement resembles a sponge, or a mass of soap foam, or a vast net cast across the dark. This forces a strange reversal of scale. We are used to thinking of a galaxy as the grandest object in nature, a wheeling city of 100 billion stars. But a galaxy is only a single bright bead threaded on the web, and the thread it hangs from is larger than the galaxy, by as much as the galaxy is larger than one of its stars. The biggest structures of all, the great walls where filaments and clusters gather, stretch across more than 1 billion light-years. Light, which takes 100,000 years just to cross our own galaxy, needs more than 1 billion years to traverse one of these walls. There is nothing larger. The cosmic web is the final tier of structure, the topmost pattern the universe builds, and above it, there is only the uniform thinning out of everything into the distance. We did not learn this from any single photograph, because the web only reveals itself when you know how far away each galaxy lies. On the flat sky, a nearby galaxy and a distant one sit side by side, and the structure is hidden in the flattening. The breakthrough came from measuring distances, galaxy by galaxy, using the stretching of their light by cosmic expansion to gauge how far each one sat, and so building a true three-dimensional map. In the 1980s, astronomers patiently measured the distances to a few thousand galaxies within a single thin slice of sky, expecting many of them a fairly even scatter. What they found instead stopped them short. The galaxies traced out sharp arcs and long walls curving around great empty circles, exactly as the film of soap traces the surfaces of bubbles in a glass. One immense sheet of galaxies they charted was so large that they simply named it the Great Wall. Later surveys grew vastly more ambitious, charting the positions of millions of galaxies across enormous volumes of space. And as they did, the web emerged in its full glory. The same branching architecture of filament and knot and void, repeating through every region they mapped. The greatest of them swept methodically across huge swaths of sky for years on end, recording the position and the distance of one galaxy after another until the catalog ran into the millions, building, in effect, the first true atlas of the universe at its largest scale. And every region it charted told the same story. Filament, wall, and void, the same lacework wherever it looked. These maps are among the most quietly astonishing images science has ever produced. Each point of light in them is not a star, but an entire galaxy. Hundreds of billions of stars reduced to a single dot, and the dots, in their millions, arrange themselves into a delicate, glowing lacework of threads and walls wrapped around yawning hollows. No one drew it. No one expected it. It was simply there, waiting in the data, once we had eyes large enough to take it in. So why this shape, of all shapes? Why threads and knots and hollows, rather than an even scatter or a field of round blobs? The cosmic web is not a coincidence and not an ornament. It is the precise and very nearly inevitable form that gravity produces when it amplifies those faint initial ripples we saw in the ancient light. And the reason it comes out woven, rather than lumpy, lies in the way an irregular region collapses. A patch of the early universe that is slightly denser than average is almost never a perfect sphere. It is a little lopsided, slightly longer in one direction than in the others, as real things always are. And gravity does not pull such a patch inward evenly. It collapses fastest along the patch's shortest direction, the way a slightly squashed ball of dough flattens first along the line where it is already thinnest. So the region falls together first into a flattened sheet, a great cosmic pancake. Then the matter spread across that sheet drains inward along its next shortest direction, gathering itself into a long, dense filament. And finally, the matter strung along the filament slides toward the places where filaments cross, piling up into the massive knots that become the clusters. Sheet, then thread, then knot, each stage feeding the next. The web is simply what you get when countless slightly irregular regions collapse under gravity in this same ordered sequence all across the universe at once. And this is not a finished event, but an unfinished one, still underway. The web is sharpening even now. Matter is still draining out of the thinning regions. still creeping along the filaments toward the great clusters, still piling up at the crossing points. We are watching the structure midway through its construction. A building that has been rising for 14 billion years is not yet complete and will go on slowly growing for as long as gravity has matter left to gather. The empty voids are the other half of the same story, and they were carved by the same hand. The regions that happened to begin slightly underdense had slightly weaker gravity than their surroundings, and so, as the dense regions pulled matter in, the thin regions could not hold on to their own. They surrendered their matter to the filaments and clusters forming around their edges, and over billions of years they have been steadily draining and swelling, pushed wider by the expansion of the universe and emptied by the gravity of everything around them. A void is not a hole punched into the web. It is the place the web was drained from, the quiet emptiness left behind, once gravity had pulled its contents out to the bright edges. It is hard to overstate how empty these places are. A galaxy adrift in the middle of one of the largest voids would lie so far from its nearest neighbors that to human eyes it might seem to sit utterly alone in the cosmos, its night sky all but starless beyond its own stars. For most of the history of astronomy, we pictured space as more or less evenly populated. The voids show that most of the volume of the universe is, in truth, profound emptiness, and that matter huddles together on the thin partitions between the hollows. So the cosmic web was never painted onto space. It precipitated out of it, like frost spreading across a cold pane of glass in branching, repeating fronds, like crystals forming in a cooling solution, like salt left behind in delicate ridges as a pool of seawater dries. The web is matter settling out along the lines that gravity and the initial seeds laid down between them. A once smooth haze, given a force that only attracts and billions of years to apply it, does not stay a haze. It crystallizes into threads and nodes and hollows, by nothing more than the patient arithmetic of pulling together. There is no blueprint anywhere in this. There is only an attractive force, a field of faint imperfections, and time. And out of those three, the grandest structure in existence assembles itself. And when the simulations of gravity we spoke of earlier are run forward and then laid against the real maps, they reproduce not merely something web-like, but the web's exact statistics. The right number of voids at the right sizes, the right tally of filaments, the right way the threads link knot to knot. The agreement is detailed and quantitative, and it is the strongest sign we could ask for that we genuinely understand how this immense thing came to be. And the shape it assembles into is uncanny. Seen in the great maps, the cosmic web looks startlingly like other things, like the branching tangle of nerve cells in a brain, like the threads of a fungus spreading through the soil, like the foam standing on a poured drink. The largest structure in the universe bears a clear family resemblance to some of the smallest and most intricate structures found within it. That resemblance is not a trick of the eye, and it is not a coincidence either. It points to something deep about how nature builds, which we will come back to. For now, simply hold the image. The universe, at the very limit of its scale, looks woven, threaded, almost grown. The cosmic web, then, is the runaway's finished masterwork. The faint ripples of the cosmic microwave background grown to their full and final size, order on the largest scale that order exists. It was assembled with no plan, out of the slightest unevenness imaginable, by a single tireless force. But notice that the web is built of galaxies, the bright beads strung along its threads. And if we stop sweeping our gaze across the whole vast structure and drop down instead to one of its glowing knots, to look closely at the galaxies themselves, we find that the pattern does not stop at the web. It carries on downward. The galaxies, too, repeat their forms, falling again and again into the same few shapes, and they do so for reasons entirely their own. Look closely at the galaxies, and you find, once again, a small repertoire of shapes repeated without end. There are the grand spirals, flat rotating disks of stars with luminous arms sweeping outward in slow, graceful curves. The kind of object most people picture when they hear the word galaxy. There are the ellipticals, smooth and featureless. Great rounded swarms of stars shaped like balls or eggs, with no disk and no arms. Only a quiet glow that fades from a bright center to dim edges. And there are the irregulars, the smaller and more ragged ones that fit neither mold. But the striking thing is how few categories there are. Survey the galaxies in their tens of billions, scattered across the entire observable universe, and very nearly all of them fall into this handful of families. Once you have seen one spiral, you recognize the next, and the next, across distances so great that the light of each one left it before the Earth existed. The forms repeat, faithfully, everywhere. And as with everything else in this story, the shapes are not chosen. They are outcomes. To see why a galaxy becomes a spiral, begin with the fact that the cloud of gas it forms from is almost always turning, however slowly, to start with. Nothing in the universe is perfectly still, and a vast cloud drifting in the early cosmos will have some small rotation, some faint overall spin, inherited from the tugging of its neighbors. Now let gravity pull that cloud together. As it shrinks, something has to give, because there is a rule that spinning things obey without exception. As a turning object draws its mass inward, it must spin faster to compensate. You have seen this rule in action whenever a figure skater pulls in her arms and accelerates into a blur, or a diver tucks into a tight ball and tumbles faster. The same thing happens to the collapsing cloud. As gravity draws it inward, its lazy initial turn winds up into a genuine spin, faster and faster as it shrinks. That spin is what flattens the galaxy into a disk. Picture the cloud collapsing. Along the axis it spins around, top and bottom. There is nothing to stop the gas from falling straight inward, and so it does, the cloud squashing down from above and below. But out at the spinning edge, the rotation flings the gas outward, resisting the inward pull, holding it up against gravity. So the cloud cannot collapse evenly to a point. It falls in along one direction and holds station in the other, and the result is a disk, thin and wide and turning, like a lump of pizza dough flung spinning into the air, which spreads into a flat circle for exactly the same reason. Nearly every spiral galaxy in the universe is a disk made this way, gravity pulling inward, spin holding the rim out, the two settling into a turning plate of stars. Where then do the round ellipticals come from if spin makes a disk? They come from a shortage of spin, or from violence. A cloud with very little net rotation has nothing to flatten it, and collapses into a rounded blob rather than a disk. And when two great spiral galaxies collide and merge, as happens across cosmic time, the orderly rotation of each is scrambled in the wreck. The stars are flung onto every kind of path at once, their motions randomized, and what settles out of the merger is not a fresh disk, but a smooth, featureless ball, an elliptical. The shape a galaxy wears, in other words, is a record of its history, how much it was spinning, what it has collided with, how its matter came together. Same physics throughout, different inputs, and so a small range of different but always recognizable results. This is not only ancient history, it is also our own future. Our galaxy and the Great Spiral of Andromeda, the nearest large galaxy to the Milky Way, are falling toward each other and will meet a few billion years from now. When they do, the two disks will be pulled apart and reworked, their orderly rotations scrambled in the encounter, and out of the long, slow collision, a single rounded elliptical will eventually settle. The spiral we live in, dissolving into a smooth swarm of stars. The very process that shaped the ellipticals we see scattered elsewhere is already on its way to remaking us. The spiral arms deserve a closer look because they hide a lovely subtlety. It is natural to imagine the arms as solid structures, fixed strings of stars curving out from the center. But they cannot be, and a simple argument shows why. The inner parts of a galaxy's disk orbit faster than the outer parts. So if the arms were fixed ribbons of the same stars, they would wind up tighter and tighter with every turn, coiling into nothing within a few rotations, and the grand open spirals we see could not last. They do last. So the arms are not fixed objects at all. They are patterns, waves of slight crowding that sweep through the disk, regions where stars and gas pile up a little, the way cars bunch into a slow-moving knot on a motorway. A particular car enters the traffic jam, crawls through it and leaves, while the jam itself stays put on the road. In the same way, stars drift into a spiral arm, linger in the crowding and pass out the other side, while the arm pattern persists. And where the gas is squeezed in that crowding, new stars are born, blazing and bright, which is why the arms glow, lit by fresh young stars marking out the wave. The arm is a pattern moving through the stars, not a thing made of fixed stars, a pattern within the larger pattern of the disk. Step back from the details, and the deeper point is the one we keep returning to. The galaxies repeat their forms for the same reason everything in this story repeats. The same physics, acting on similar starting conditions, produces the same results over and over, with no need for a plan. A galaxy does not choose to be a spiral. Spiral is simply what a turning cloud of gas becomes when gravity pulls it together, every time, whether it happens here or in a galaxy whose light has been traveling toward us since before the sun was born. The rule that spins up a collapsing cloud is the same rule everywhere. The force that flattens it is the same force everywhere. And so the outcome is the same outcome everywhere, 100 billion times across the sky. The universe is not endlessly inventing new designs for galaxies. It keeps solving the same problem, and the same problem has the same solution. And because these same forms appear in galaxies whose light has crossed almost the entire age of the universe to reach us, we know the rules that shape them have not drifted across all that time. A spiral assembled 10 billion years ago was assembled by the same physics that assembles one today. The repertoire is fixed because the rules behind it are fixed. We are living inside one of these solutions. Our own sun is one star among a few hundred billion in a great spiral galaxy, the Milky Way, riding within its disk, carried around the center once roughly every 250 million years. A single galactic turn so slow that the last time the sun sat where it sits now, the earliest dinosaurs were just appearing on Earth. We do not see our galaxy's spiral from outside, only its glowing edge smeared across the night sky, the band of light that gave the Milky Way its name. But we know its shape because it is the same shape worn by countless others, built by the same collapse and the same spin. We are not observers standing outside the repeating forms of the cosmos. We are riding within one of them. And yet, for all this sameness, no two galaxies are identical. Each has its own particular arrangement of arms, its own history of mergers, its own scattering of brighter and dimmer regions, its own exact number and arrangement of stars. The repetition is in the family, not in the individual. The universe produces spirals the way a forest produces oak trees, every one unmistakably an oak, no two precisely alike. Variation decorates the pattern without ever erasing it. The deep form repeats. The surface detail is always fresh. Notice, though, what every step of this explanation has quietly leaned on. To flatten the disk, we used a rule, that a spinning thing keeps spinning and spins faster as it draws inward, that its spin is conserved and cannot simply vanish. We have used rules like this one again and again, here and all through the story, treating them as bedrock, as simply the way things are. But why should they be? Why should a spinning cloud conserve its spin at all? Why should anything in the universe be conserved, held fixed, never created or destroyed? We have traced the patterns of the cosmos down through the web and the galaxies to the rules that produce them. And now we have arrived at the rules themselves and at the deepest question this whole journey contains. Why are there unbreakable rules in the first place? The answer is the most beautiful idea in physics, and when you first understand it, the ground seems to shift beneath you. The answer is a single word that does not at first sound equal to the task: symmetry. To most of us, the word means a pleasing balance, the matching halves of a face, the mirrored wings of a butterfly, the 6 identical arms of a snowflake. That everyday meaning is real enough, but physics has taken the word and sharpened it into something far more powerful, and once you see the sharpened version, you begin to find it everywhere, quietly holding the universe together. In physics, a symmetry is any change you can make to something that leaves something else unchanged. Take a perfect square. Turn it by a quarter turn, and it looks exactly as it did. You could not tell it had moved at all. That unchangedness under rotation is the square's symmetry. A circle has more of it. Turn a circle by any amount whatever, and it is utterly unaltered. A blank sheet of paper, slid sideways, looks just as it did before you slid it. In each case, there is some change you are allowed to make, a rotation, a shift, under which the thing stays identical to itself. Symmetry, in this precise sense, is sameness that survives a change. It is a kind of indifference, a refusal to be altered by something you might have expected to matter. It is a strange and useful inversion of how we usually think. We normally describe a thing by what makes it distinctive. Symmetry describes it instead by what fails to make any difference to it. The more symmetric something is, the more changes leave it untouched, and so, in a sense, the less there is to say about it. Because so much about its situation simply does not matter. A circle does not care how you turn it. A blank sheet does not care where you slide it. This not mattering, this wide indifference to change, can sound at first like emptiness, like absence. It is in fact one of the most generative facts in all of nature, and very nearly the whole of the order we have been tracing flows out of it. Now comes the move that turned this from a fact about shapes into one of the deepest ideas in all of science. Stop applying symmetry to objects and apply it instead to the laws of nature themselves. Ask not whether a square looks the same when you turn it, but whether the rules of physics stay the same when you change the circumstances under which you put them to the test. And they do, in 3 sweeping ways, each one so familiar that we go through our whole lives without once remarking on it. First, the laws are the same at every moment in time. Perform an experiment today. Measure how a ball falls, how a current flows, how a beam of light bends, and then perform the identical experiment next week, next year, 1,000 years from now, and you will get the identical result. Physics does not keep a calendar. It does not run one way on Tuesday and another on Friday, nor behave differently in this century than it did in the last. The rules are wholly indifferent to when you apply them. Slide the entire experiment forward or backward in time, and nothing about its outcome shifts. That is a symmetry of the laws under a change of moment. Second, the laws are the same at every place. Carry your equipment across the room, across the country, to the far side of the earth, to the surface of the moon, to a galaxy 10 billion light years away, and the same experiment yields the same answer. We have, in fact, already met this symmetry once, when the light of distant stars told us that hydrogen behaves identically across the whole universe. That was precisely this symmetry, showing its face. Physics carries no map with special locations marked upon it, no privileged spot where the rules are different. Slide the whole experiment from here to anywhere else at all, and the result is untouched. That is a second symmetry under a change of place. Third, the laws are the same in every direction. Set up your experiment facing north, then swing the entire apparatus around to face east, or to point straight up at the sky, and it behaves exactly as it did before. Space has no preferred direction woven into its laws. no cosmic up or favored bearing that physics respects above the others. Turn the whole thing to aim any way you please, and nothing whatever changes. That is a third symmetry, under a change of direction. Each of these sounds almost too obvious to be worth saying aloud. Of course the laws are the same tomorrow as today. Of course they are the same across the room. Of course they do not care which way you happen to be facing. But linger on that obviousness, because it is concealing something important. Not one of these had to be true. We can imagine, with no contradiction at all, a universe whose rules drifted as the ages passed, so that gravity pulled a little harder in one epoch than the next. Or a universe with a special place at its heart where physics ran by different rules. Or one with a favored direction along which everything fell a little more easily. Such universes are not nonsense. They are merely not ours. Our universe happens to possess these symmetries. The laws are genuinely, precisely indifferent to when, and where, and which way, and that indifference is among the deepest and most particular facts about the place we live. It is worth seeing how much rests on those three indifferences, because without them, knowledge of the world would be impossible. If the laws drifted with time, no experiment could ever be repeated and trusted, since the result you got today would tell you nothing about tomorrow. If they varied from place to place, a measurement made in one laboratory would say nothing about any other, and there could be no general truths, only local ones. If they depended on direction, the universe would have to be studied afresh for every way of facing. The entire possibility of science, of finding rules that hold beyond the single instance, rests silently on the fact that the laws are symmetric. We could only ever discover lasting laws because lasting laws were there to find. And this, you may notice, is the very same point we reached long ago from the opposite direction, now named at last with its proper name. We said that patterns exist because the same causes produce the same effects, always and everywhere. To say that is simply to say that the laws do not change across time, or across space, or with direction, which is to say that the laws are symmetric. The repeatability of the universe, the thing that lets the night sky keep its appointments, and the same elements glow identically across every galaxy, is the outward face of these inner symmetries. Symmetry is the exact and proper name for the consistency we have been circling this entire time, and symmetry runs deeper still than these three. When physicists looked closely at the forces themselves, at electricity and magnetism, at the forces locked inside the atomic nucleus, they found that each one springs from a symmetry of its own, a more abstract sameness, under change buried in the equations. The forces of nature are not arbitrary furniture added to the world. They are, in a sense we are still learning to state plainly, demanded by symmetries. The deeper physicists dig, the more of the universe turns out to be symmetry, wearing a disguise. But naming it, however satisfying, is not the astonishing part. The astonishing part is what these symmetries turn out to be secretly bound to, a connection proven, as a piece of airtight mathematics, just over a century ago. Each of these indifferences of the laws, to the moment, to the place, to the direction, is tied by unbreakable necessity to a particular quantity in the universe that can never change, never be created, and never be destroyed. The symmetries of the laws and the great conservation laws of physics, the iron rules declaring that certain quantities are fixed for all time, are not two separate collections of facts that happen to sit side by side. They are the same facts, viewed from two different sides. The indifference of the laws to the passing of time turns out to be the very reason that energy can never be created or destroyed. And the spin we leaned on to flatten the galaxies turns out to be conserved for a reason of exactly the same kind. The person who proved this precise, world-altering connection, who showed in rigorous detail how an abstract symmetry becomes an unbreakable law of conservation, was a mathematician whose name deserves to stand beside the greatest in the history of science, and whose theorem is where this entire journey finally touches its floor. Her name was Emmy Noether, and she was one of the most powerful mathematicians of the 20th century, though the world she worked in did its best not to notice. In the Germany of the early 1900s, a woman could not hold a professorship. And so for years, she lectured at the great University of Göttingen without pay. Her courses listed under a male colleague's name because the rules forbade her own. When the faculty objected to granting her a position on the grounds that she was a woman, the mathematician David Hilbert is said to have retorted that a university was a place of learning, not a bathing house, and that he could see no reason a candidate's sex should count against her. Years later, she would be driven out of Germany altogether by the Nazis for being Jewish and would live out her life in exile. Einstein, who was not free with such praise, called her the most important creative mathematical genius the world had produced since the higher education of women had begun. It was a specific puzzle that drew her to the very heart of physics. Einstein had just unveiled his new theory of gravity, and it carried a confusion with it. In that strange new picture of curved space and time, the cherished principle that energy is conserved seemed to behave in slippery and troubling ways, and some of the finest minds of the age could not see clearly why. Noether was asked to look into it. What she produced in answer was not a patch for that single problem, but a result of enormous generality, a theorem that laid bare the true relationship between symmetry and conservation across the whole of physics, and in doing so, dissolved the original puzzle almost as an afterthought. In 1918, she proved a theorem so deep that it quietly reorganized how physicists understand their own subject, and it is the theorem that completes our story. What Noether proved, in full and unassailable rigor, is this. For every continuous symmetry of the laws of nature, there exists a quantity that is conserved, something that can never change, never grow or shrink, never be created or destroyed, for as long as that symmetry holds. Symmetry on the one side, an unbreakable conservation law on the other, and an exact, provable bridge running between the two. Wherever the laws are indifferent to some change, something in the world is thereby locked, held fixed for all time. The symmetries we met are exactly the kind her theorem feeds on, the kind you can apply by any amount you like, smoothly and without a break. You can slide time forward by a second or by a century, shift position by an inch or by a light year, turn through any angle at all. And to each of these smooth indifferences of the laws, Noether's theorem attaches one specific, familiar, conserved thing. Take the first, the indifference of the laws to the moment in time, the plain fact that physics runs the same today as it will tomorrow. Noether's theorem says that this symmetry, entirely on its own, guarantees the conservation of energy. The reason energy can never be conjured from nothing or made to simply vanish, the single most relied upon principle in all of physics and engineering, the rule behind every machine ever built, is precisely that the laws of nature do not depend on what time it is. Time symmetry and the conservation of energy are not two discoveries that happen to both be true. They are one truth, and Noether showed, line by line, exactly why. This is why one particular old dream has never come true. For centuries, hopeful inventors have labored to build a perpetual motion machine, a device that gives out more energy than it takes in, running forever and granting something for nothing. Every attempt has failed, and Noether tells us the failure is not a matter of insufficient cleverness. It is forbidden in principle. So long as the laws of physics stay the same from one moment to the next, and they do, energy cannot be created, and no machine, however ingenious, will ever conjure it into being. The dream is ruled out not by engineering, but by the symmetry of time itself. Take the second, the indifference of the laws to place. This symmetry guarantees the conservation of momentum, the quantity of motion. The reason a moving object sails onward in a straight line until something pushes it, the reason a rocket lurches forward as it hurls its exhaust backward. Because the laws of nature do not care where in space you happen to be. The momentum of the universe is fixed and forever accounted for. And take the third, the indifference of the laws to direction. This one guarantees the conservation of angular momentum, of spin. And here a loop we left hanging long ago snaps shut. We said, watching the galaxies take shape, that a collapsing cloud must turn faster as it draws inward, because its spin is conserved, and we took that conservation simply as given. Now we can say why it holds. Spin is conserved because the laws of physics are the same in every direction. The flattening of every spiral galaxy in the sky, the blur of the skater pulling in her arms, the steady turning of the Earth beneath the night, all of it traces back, through Noether's theorem, to the bare fact that space plays no favorites among directions. Stop and feel the strangeness of this, because it is genuinely vertiginous. It is not obvious, it is not even faintly intuitive, that the statement "the rules do not care what time it is" should force the entirely different statement "energy can never be created or destroyed." The first is a remark about the indifference of the laws. The second is a hard practical limit on what the universe is permitted to do, a constraint obeyed by every engine, every star, every flicker of chemistry in every living cell. That the one should compel the other by airtight mathematical necessity is the kind of result that seems, when you first take it in, to tilt the floor beneath you. The great conservation laws, the bedrock certainties of physics, the quantities you can always count on, are not a list of separate commandments handed down one by one. They are the shadows cast by the symmetries of the laws. Each indifference throws its own conservation law, the way a shape throws a shadow. Nor does the bridge carry only these three. The same theorem reaches the deeper symmetries hidden inside the forces, the ones we glimpsed a moment ago. Out of the symmetry behind electricity and magnetism, for instance, flows the conservation of electric charge, another quantity the universe guards jealously and never loses. The whole austere bookkeeping of physics, the short, strict list of things that are never created and never destroyed, turns out to be symmetry, written in another hand. And with that, the whole journey arrives at its floor. Why does the night sky keep its appointments? Why could gravity spend billions of years patiently raising the cosmic web, never once finding the rules changed under its feet? Why does a hydrogen atom shine the same color in every galaxy? Why did spin flatten the galaxies into disks? Every one of these, followed down far enough, comes to rest on a single foundation. The laws of nature do not depend on when or where or which way, and by Noether's theorem, that threefold indifference locks in the conserved quantities that allow anything at all to persist, to recur, to be relied upon. The universe has patterns because its laws are symmetric, and symmetry, carried across Noether's bridge, becomes the conserved quantities that hold each pattern in its place. That is the answer the question demanded. That is the bottom of it. There is something almost too clean about this, and it is only honest to admit the mystery still tucked inside it. We have explained the patterns by the conservation laws, and the conservation laws by the symmetries. But we have not explained why the laws should be symmetric in the first place. That, so far, is simply how our universe is built, the deepest fact we have managed to reach, the floor below which we cannot yet see. But standing on that floor, we can finally turn back around. We came down a long way to get here, through the web, the galaxies, the rules that shape them, to reach this bedrock of symmetry and conservation. Now, with the foundation in hand, we can climb back toward the daylight and look once more at the sheer riot of repeated forms the universe actually wears, and ask a new question of it. Not why patterns exist, which we have answered, but why the very same patterns keep reappearing at wildly different sizes, nested inside themselves, from the cosmic web down to the branch of a tree and the vein in a leaf. The universe does not merely repeat. It repeats itself across the scales, echoing its own designs from the largest things in existence down to the smallest, and that echo has a name. The name is self-similarity, and the shapes that possess it are called fractals. A fractal is a structure that looks much the same at different scales, so that when you zoom in on a part of it, you find a smaller copy of the whole, and when you zoom in on a part of that, another copy again. The same form nested inside itself, like a set of dolls that never quite reaches the smallest doll. Once you have learned to recognize it, you begin to see it everywhere in the living and the non-living world alike. And its sheer ubiquity is one of the great quiet clues to how the universe builds. A fern is the cleanest illustration. A whole fern leaf is made of smaller leaflets, and each leaflet repeats the shape of the entire leaf. And each of those is built in turn from still smaller leaflets of the very same shape. Snap off a single frond, hold it on its own, and it looks like a complete miniature fern. A head of Romanesco, that pale green spiraled vegetable, is a cone built of smaller cones, each shaped like the whole, each built of smaller cones again. A tree divides its trunk into boughs, its boughs into branches, its branches into twigs, every division echoing the one before. Lightning forks, and each fork forks again in the same jagged manner. A river seen from high above splits into tributaries that split into streams that split into rivulets, the same branching repeated at every scale. The same shape, folded inside itself, from the large down to the small. The mathematician who gave these forms their name, Benoit Mandelbrot, captured the idea with a deceptively simple question. How long is the coastline of a country? It sounds as though it ought to have a definite answer, and it does not, and the reason is self-similarity. Measure a coastline with a long ruler, stepping off segments a mile at a time, and you get one length. Measure it again with a shorter ruler, and you pick up all the bays and headlands the long ruler stepped straight past, and the coastline comes out longer. Measure it with a shorter ruler still, and you catch the coves inside the bays and the notches inside the coves, and it grows longer yet again. A coastline is crinkled at every scale, jagged whether you view it from orbit or crouch down to study a single stretch of rock, and so its measured length depends entirely on the size of your ruler, climbing without limit as the ruler shrinks. There is detail all the way down. That endless nested roughness is the very signature of a fractal. So why is nature so fond of these self-repeating forms? The answer reaches to the heart of everything we have been saying. A fractal is what you get when a simple rule is applied over and over, at one scale after another. Take a single instruction, split in two and grow outward, and apply it to a trunk, and you get two boughs. Apply the very same instruction to each bough, and you get branches. Apply it once more to each branch, and you get twigs. One rule, repeated at every scale, and out of it comes a tree. The self-similarity is not painted on afterward. It is the direct fingerprint of a process that does the same thing regardless of size. Where you see a fractal, you are looking at a single rule that does not care how large or small the thing it acts upon happens to be, repeating itself down through the scales. The purest demonstration of this lies in mathematics itself, in the famous shape that carries Mandelbrot's own name. It is produced by a formula short enough to write on a fingernail, a single arithmetic step repeated over and over. And yet the shape it draws is infinitely intricate, fringed with spirals and filaments and curling tendrils. And if you magnify any patch of its edge, you find more detail, and buried within that detail, tiny, perfect copies of the entire shape at every depth forever. Endless complexity, with no end of surprises, flowing out of one simple instruction applied without stopping. It is the whole principle held in miniature. Repeat a simple rule enough times, and richness beyond reckoning appears unbidden. And many of nature's fractals are solving the very same problem, which is why they end up looking so alike. Consider how much of life depends on spreading something through a volume, or gathering it in from one. A tree must spread its leaves to catch sunlight across the widest possible reach, and carry water and sap to every one of them. Your lungs must bring air into contact with blood across an enormous surface, folded somehow into the space of your chest. Your circulatory system must carry blood to every living cell in your body and bring it back again. The efficient answer to all of these is identical. Branch and branch again, and keep branching, so that a single trunk can reach into every corner of a space through finer and finer divisions. That is why the airways of your lungs, the vessels of your blood, the boughs of a tree, and the channels of a river delta all wear the same branching, fractal form. They are different materials moving different things, but they are all answers to a single problem, the problem of reaching everywhere from one place, and the answer to that problem is a fractal. The lungs are a small marvel of exactly this. Branching some 20 times over from the windpipe down to the tiniest air sacs, they pack a surface for exchanging gases that, if it were spread out flat, would cover something close to the floor of a tennis court, all folded quietly into your chest. Nature reaches that vast surface not by drawing up an elaborate plan in advance, but by repeating one branching rule until the available space is filled. This is the economy at the very heart of self-similarity. The universe does not need a separate blueprint for each scale. It finds one rule that works, applies it again and again at every size, and lets the nesting do the rest. It is a way of generating enormous complexity, almost for free, out of nothing more than repetition. This is one of nature's favorite tricks, and it is everywhere once you start to look. The spiral of a shell laid down by a single rule of growth, the body of a developing creature unfolding from a short genetic recipe, the endless variety of snowflakes, each one six-armed and self-similar, each grown by the same rule applied as it tumbled through the cloud. In every case, a great deal of structure is conjured out of very little rule, simply by letting the rule run. And now we can return to a resemblance we noticed earlier and deliberately set aside. The cosmic web, we said, looks uncannily like other things entirely. The branching of neurons in a living brain, a fungus threading its way through soil, the foam standing on a poured drink. We can finally say why, and the reason is not that the universe is secretly a brain, or that it is in any sense alive. It is that all of these structures are built by processes that branch and cluster and link into networks, and branching, clustering processes leave behind self-similar, web-like forms wherever they occur. Whether the thing doing the branching is gravity drawing matter into filaments, or a fungus creeping toward its food, or neurons reaching out to find one another. Different forces, different materials, different scales, separated by a gulf almost beyond imagining, and yet the same geometry at the end. Because the same kind of process leaves the same kind of shape. The largest structure in the universe rhymes with some of the smallest living ones for the plainest of reasons. Nature, once again, is reusing a solution that works. It would be dishonest not to add a caution. Nature's fractals are not the flawless, endless fractals of pure mathematics. They repeat over a range of scales, and then they stop. The branching of a real tree runs out after a dozen or so divisions, and the self-similarity of the cosmic web gives way, at the very largest scales of all, to the smoothness we began this whole story with. But over the range where it does hold, the rhyme is real, and it is astonishing. A fern frond, a bolt of lightning, a river delta seen from orbit, the airways folded inside your chest, and a slice of the cosmic web, hundreds of millions of light years across, all carry the same nested, branching signature. The universe echoes its own designs across a span of sizes so enormous that one shape can link a thing you hold in your hand to a thing that light needs ages upon ages to cross. This is self-similarity, and it is the deepest expression yet of the theme we have followed from the very first night sky. The same rules, shown now to care as little about scale as they do about time, or place, or direction, producing the same forms at every size they touch. The universe is economical and patient and endlessly repetitive. And out of that repetition comes all the structure we have surveyed, from the atom to the web. And yet a shadow falls across this whole picture of building and ordering and growing, and it is time at last to face it. There is a law of physics, perhaps the most famous law of all, that declares the universe is not winding up but running down, sliding without rest from order into disorder, from structure toward formless decay. If that law is true, and it is among the surest we have, then how can the cosmos be so brimming with exquisite, intricate, growing order? How can a universe that is falling apart spend its time assembling galaxies and ferns and lungs and living things? The resolution of that paradox is one of the most beautiful ideas in all of science. The law is the second law of thermodynamics, and in plain words, it says that the disorder of the universe as a whole can only ever increase. Physicists measure disorder with a quantity called entropy, and the second law states that the total entropy of the universe never falls. Left to itself, it climbs, always, without a single known exception. Heat flows from hot things to cold things, and never the reverse. A drop of ink released into a glass of water spreads until it is evenly mixed, and never, in the entire history of the universe, gathers itself back into a drop. A sandcastle slumps into a heap, and a heap of sand has never once assembled itself into a castle. Drop a wine glass and it shatters. No one has ever watched the shards leap up and knit themselves whole. The universe has a direction, and the direction is toward disorder. The reason is not some force dragging things toward chaos. It is something subtler and, once seen, undeniable. Disorder is simply far more common than order. For almost anything, there are only a few ways to be ordered and an overwhelming number of ways to be disordered. Take the shuffled deck of cards again. There is exactly one arrangement in which the cards run in perfect order, and the number of disordered arrangements is so enormous it beggars description. Shuffle an ordered deck, jostle it at random, and it will come out disordered very nearly every time. Not because shuffling hates order, but because the disordered arrangements outnumber the ordered ones so absurdly that chance lands on disorder essentially always. Now scale that up to the countless particles of the whole universe, ceaselessly jostling and colliding, and the result is the second law. Things drift toward disorder because there is so overwhelmingly much more disorder to drift into. This is also what gives time itself its direction. It is a curious fact that almost all the deepest laws of physics run equally well forwards or backwards. Watch a film of two billiard balls colliding and bouncing apart, and you cannot tell whether it is playing forwards or in reverse. Both look entirely natural. But watch a film of a glass shattering on the floor, then run it backwards, and the absurdity is instant. Shards leaping up off the tiles, knitting themselves into a glass, hopping back onto the table. We know at once that time has been reversed, and the one thing that tells us is the second law. The shattering increases disorder. The unshattering would decrease it, and that simply never happens. The flow of time we feel, the difference between a settled past and an open future, the fact that we remember yesterday and not tomorrow, all of it is the one-way climb of entropy turned into experience. The arrow of time is the arrow of disorder. So here is the paradox in its full strength. The universe is sliding, without rest and without reversal, toward ever greater disorder. And yet it is filled to overflowing with order, with galaxies and stars and crystals and ferns and the staggering intricacy of living things. How can a cosmos running downhill into disorder be so endlessly busy building exquisite structure? How is any of the order we have spent this whole journey admiring even possible? If the deepest tendency of the universe is to come apart, the resolution hides in three small words in the law itself: as a whole. The second law forbids the total disorder of everything from decreasing. It says nothing whatever against disorder decreasing here in some particular corner, so long as it increases by more than that somewhere else, keeping the grand total climbing. Order can be built locally, in a pocket, on an island, provided the building dumps a larger measure of disorder into the surroundings. The books must balance, and across the whole they must always rise, but in one ledger, in one place, they are perfectly free to fall. Order is not forbidden. It is permitted on a single condition, that it be paid for. You can watch this bargain at work in your own kitchen. A refrigerator makes a cold, orderly little world inside itself, holding back the disorder that would otherwise warm and spoil its contents. But it does not do this for free. Reach behind it, and you will feel the warmth pouring off its coils, more heat, and so more disorder, pumped out into the room than was ever removed from inside. The fridge lowers the disorder within by raising it further without, so that the kitchen as a whole, and the universe as a whole, ends up more disordered than before. Every island of order in the cosmos runs on some version of that same deal. And the great engine that pays for the order around us is the star. A star is a magnificent island of order, a tightly organized ball of matter held in its long truce between gravity and fire. But look at what it does to maintain that order and to power the order of everything near it. It takes in concentrated energy, a small number of intensely energetic events deep in its core, and it pours out in exchange a vast flood of light, an immense number of far lower grade parcels of energy streaming away into the cold and the dark. For every concentrated unit of order it spends, it scatters a far greater quantity of disorder into the surrounding void. The sun is not breaking the second law. It is obeying it lavishly, paying for its own existence, and for the existence of everything it warms, by exporting a great tide of disorder into the night. And every ordered thing on earth runs on that same bargain. A plant builds itself, an exquisitely ordered structure, by capturing the concentrated light of the sun and using it to assemble ordered molecules, degrading that high-quality light into waste heat as it goes. An animal eats the plant and builds its own order, and sheds heat in its turn. Every living thing, every forest and city and human body, is a small eddy of order spinning upstream against the current of the second law, and every one of them is funded, in the end, by the sun pouring its energy downhill into space. We are not exceptions to the slide toward disorder. We are paid for by it. The order of life is bought with the far larger disorder the sun broadcasts endlessly into the cold. You can even count the cost. The sun sends the earth a modest stream of high-energy particles of light, the bright visible photons of daylight, and the earth, having put them to use, radiates their energy back out to space as a far greater number of feeble, low-energy photons of heat. Almost all of the energy is returned, the books on energy balance. But it leaves as many more and much poorer parcels than arrived, and that multiplication of parcels is precisely the disorder increasing. Life lives in the gap, in the brief passage between the arrival of the rich light and the departure of the poor, and uses the difference to hold itself together. Now step back to the whole universe, and a surprising and beautiful thing swims into view. We made much, early on, of how astonishingly smooth the young universe was, and we praised that smoothness. But where gravity is in command, the everyday sense of order and disorder turns over. For matter ruled by gravity, smooth and evenly spread is the special, ordered, low disorder condition, and clumped, lumpy, gathered into stars and galaxies is the disordered, high entropy one. Which means that the smooth early universe was a state of remarkably low disorder, a vast reserve of order to begin from, and the entire grand process of structure formation we have followed, gravity gathering, that smooth haze into webs and galaxies and stars, has been the universe's disorder steadily, inexorably rising. The cosmos has been running downhill this whole time. The galaxies and the stars and the cosmic web are not exceptions to that descent. They are what the descent looks like along the way. Order here is not the opposite of the slide into disorder. Order is the slide into disorder, caught in the act of falling. Which is why all of it is order on borrowed time. The structures of the universe are funded by the great reserve of low disorder it was born with, and that reserve, though immense, is not endless. The stars are burning through it. One by one, across spans of time that make the present age of the cosmos look like an eye blink, they will exhaust their fuel and fall dark. The gathering and the building will slow and falter and cease. And the universe will drift, in its unimaginably distant future, toward a uniform, cold, featureless stillness in which the disorder is at last as high as it can be and nothing further can ever happen. The order we live among is a passing phase, a transient brilliance partway down the long descent, beautiful in part precisely because it cannot last. And far from cheapening that order, this is exactly what explains it, and what ought to make it precious to us. The exquisite structures of the cosmos are pockets of organization, funded by the running down of everything else, lit for a while as the great endowment is spent. The slide toward disorder does not prevent structure. In a strange and quietly lovely way, it pays for it. We live in the bright, brief middle of the spending, surrounded by order the universe can afford for now, because it began so improbably smooth and is so patiently, so beautifully coming apart. And the most intricate, most improbable island of order that all this spending has so far produced, the most elaborate eddy ever found swimming against the current, is not a galaxy or a star or a crystal of unimaginable perfection. It is alive. It is us. We are the most ordered thing the cosmos is known to have assembled out of its dwindling endowment, and we are built, every atom of us, from the ashes of the very stars that did the paying. That is the last turning of this long road, and it is the one that brings the whole story home. So ask the simplest possible question about yourself. Where did you come from? Not your parents and not your species, but the actual atoms, the carbon and oxygen and iron and calcium that make up your body at this very moment. Trace them back far enough, and the answer is genuinely staggering. They were made inside stars. The early universe was a poor chemist. When the cosmos cooled out of its hot beginning, it produced almost nothing but the two lightest elements, hydrogen and helium, the simplest atoms there are, with the barest trace of a third. That was the whole of the starting inventory: hydrogen, helium, and essentially nothing else. None of the carbon that forms the backbone of every molecule in a living body. No oxygen to breathe or to bind into water. No nitrogen, no calcium, no iron. The raw materials of a person did not yet exist anywhere in creation. The universe began with the ingredients for stars, and almost nothing from which to build a human being. Everything heavier was forged later, in the only furnaces hot enough and dense enough to do the work, the cores of the stars. A star spends its long life fusing light atoms into heavier ones, hydrogen into helium first, and then, as it ages, helium into carbon and oxygen, and onward and upward through the ladder of the elements, assembling heavier and heavier nuclei in its searing interior. The carbon in your cells, the oxygen in your lungs, the nitrogen woven through every strand of your genetic code, the calcium stiffening your bones, the iron riding in your blood, were all cooked, atom by atom, deep inside stars, across millions and billions of years. Out of the plain hydrogen, the universe was handed at its birth, and then, at the ends of their lives, the stars give it all back. A star does not keep its treasure forever. When its fuel at last runs low, and its life draws toward its close, it returns the elements it has forged to space, casting them out into the dark to mingle with the thin gas drifting between the stars. Some stars let go gently, and some in tremendous violence, but the result is the same either way. The gas of the galaxy is slowly enriched, one generation of stars after another, salted with carbon and oxygen and iron that simply did not exist when the universe was young. Each generation seeds the next, and the next is built from the ashes of the last. Our own sun is one of those later stars, kindled from a cloud already laced with the leavings of earlier stars long since dead. And the same enriched cloud that made the sun made the earth as well, and everything that the earth carries. Gravity, the old gatherer, drew that seeded gas and dust together, and out of it there condensed a star and a family of planets, and upon at least one of them, in the fullness of time, life and us. The very atoms that a dying star flung out into the dark were pulled back together by gravity, across billions of years, and assembled, in the end, into a creature capable of reading this sentence. So the old line is not a metaphor or a flourish. It is a plain physical fact, as literal as anything in this whole account. You are made of stardust. The carbon in your cells was made in a star. The oxygen filling your lungs as you listen was made in a star. The iron that reddens your blood and lets it carry that oxygen was made in a star. The calcium that holds you upright was made in a star. Every single atom in your body heavier than the lightest two was forged in the heart of some sun that burned and died before the earth existed, was scattered across the galaxy, and was gathered up again to make you. We are not merely the observers of the cosmos. We are made of its oldest fire, and not from one star, but from many. The atoms that make you were not all forged in a single furnace. They were gathered from the debris of countless stars that lived and died across the long history of the galaxy, mingled together in the cloud that became the sun. The water in your body is itself a marriage of two distant epochs. Its hydrogen is older than any star, made in the first minutes of the universe, while its oxygen is far younger, cooked in some stellar core and flung out at that star's death. You are, quite literally, a meeting place of the dawn of time and the deaths of suns, a relay run across nearly 14 billion years, from the beginning, through generation after generation of stars, to the particular gathering of dust that is reading this now. And of all the things that fire has ever been gathered into, a living body is the most intricate the universe is known to have produced. We have spent all of this long road marveling at the order of the cosmos, the web, the galaxies, the crystals, the fractals. And yet every one of those is simple beside a single living cell. A living thing is order of an altogether higher kind, matter arranged so precisely and so improbably that it can draw in energy, hold its own shape against the slide toward disorder, repair its own damage, and, most astonishing of all, copy itself, passing its intricate pattern onward into the future. The same atoms as the stars, obeying the very same unchanging laws, but arranged into something that can maintain its own order and make more of it. Life is the pattern of the universe, reaching a new and dizzying level of complexity, a pattern that folds back upon itself and reproduces. It is worth dwelling on how improbable this is. To build a living cell, vast numbers of atoms must be arranged not merely into order, but into a working order, each near enough to the right place, cooperating in thousands of coordinated reactions at once, the whole arrangement maintaining and rebuilding itself faster than disorder can tear it apart. Against the overwhelming statistical tide that drags everything toward the formless and the average, life holds its exquisite, particular shape, and renews it, generation after generation after generation. It is the universe's most determined act of swimming upstream, and it has been going on, unbroken, for billions of years. And then comes the strangest turn in the entire story. Out of these patterns, following the same few unchanging laws for nearly 14 billion years, the universe eventually produced something that could turn around and understand the patterns, a particular arrangement of stardust that could look up at the night sky, recognize its order, and ask why. We are the part of the cosmos that grew complex enough to study the cosmos, the place where the universe became able to wonder about itself. The people who first trusted the wheeling of the stars and the long line of their inheritors who traced that order down through gravity and symmetry to its very floor were themselves one of the patterns they were learning to read. The pattern finder turns out to be one of the patterns. The universe in us has begun to understand its own consistency. Consider what that has meant in practice. The same arrangement of stardust that is the human mind has worked out the age of the universe, photographed the afterglow of its birth, weighed the distant galaxies, and proved, in Noether's hand, the deep link between symmetry and the conservation laws that hold everything together. The cosmos spent very nearly its whole history assembling, out of its own scattered ash, a thing that could reconstruct that history and read its deepest rules. There is scarcely a stranger fact in all of science. The order of the universe has, in one small corner, become aware of itself and set about explaining where it came from. This quietly dissolves a feeling that is as natural as it is mistaken, the sense that we stand somehow outside the universe, peering in, observers studying a cosmos that is not quite our own. We do not stand outside it. We never did, and we never could. We are made of it, gathered by it, run through and through by its laws, one configuration of its matter among countless others, no more exempt from its patterns than a galaxy or a fern. The same gravity that raised the cosmic web shaped the ground beneath your feet. The same conservation laws that hold a galaxy together hold you together. The same slide toward disorder that will one day dim the stars is the very current your living order swims against and is paid for by. We are not visitors to the universe. We are the universe itself, locally and briefly, woken into awareness. So when those first watchers looked up long ago and sensed an order in the heavens they could trust, an order worth staking a harvest and an ocean crossing upon, they were sensing something real and something far deeper than they could possibly have known. They were catching the first glimpse of the consistency at the root of everything, the unchanging laws, the unbroken symmetries, the patient arithmetic of a force that only ever adds. We have followed that glimpse all the way down, from the night sky to the bedrock of physics and back up again. And now, at the very end of the road, only one thing remains. It remains to say plainly what we have found, and what it means to live in a universe that turned out, against every easy expectation, to be neither chaos nor the careful work of any hand, but something stranger and lovelier than either. We can state the answer now, plainly, the answer the question demanded from the very beginning. The universe has patterns because its laws do not change. They do not change from one moment to the next, nor from one place to another, nor from one direction to another, nor from one scale to the next. And that deep constancy, named with its proper name, is symmetry. And symmetry, through the theorem Noether proved, is the source of the conserved quantities that allow anything at all to last, to hold its shape, to recur. From that single fact, the sheer unchangingness of the rules, everything else we have seen comes flowing out. Follow it once more in a single breath. Because the laws are the same everywhere and everywhen, the same causes produce the same effects, and so forms repeat, the sphere, the disk, the spiral, the branching web. Because gravity alone among the forces only ever attracts and never cancels, it could seize on the faintest unevenness in the young cosmos, the ripples we still see in the oldest light, and amplify them across billions of years into galaxies and the great web that strings them together. Because those same rules act the same way at every scale, the same shapes nest inside themselves, from the cosmic web down to the fork of a river and the frond of a fern. And because the universe was born in a state of rare and precious smoothness, a vast reserve of low disorder, all of this structure could be built at all on borrowed time, lit for a while as that great endowment is slowly spent. One foundation and the whole patterned cosmos rising upon it, which lets us finally answer the question we set out from, the one the ancient sky watchers could not reach. We began by noticing that order, in all our ordinary experience, comes from a designer, that a pattern implies a maker, and that the wheeling order of the heavens looked, for most of history, like the surest proof of a hand behind the world. We can see now that it is neither of the two things we instinctively reach for. The universe is not chaos. It is far too lawful, too repetitive, too exactly and reliably patterned for that. But neither is it craftsmanship. No hand arranged the galaxies, no blueprint set out the web, no maker drew the spiral arms. It is a third thing, and a stranger one than either. An order that assembles itself with no plan and no planner, out of nothing more than a handful of unchanging rules and the long patience of deep time. The order built itself. Given those rules, it could not have done otherwise. This is genuinely hard to hold in the mind, because we are built to think in terms of makers. When we meet order, we look for whoever ordered it. When we meet a pattern, we look for the hand that drew it. The universe asks us to set that instinct gently down. The spiral was not designed, and it was not an accident. It is what gravity and spin must together produce. The web was not woven, and it was not random. It is what an attractive force must build from faint beginnings. Again and again, the honest answer is the same uncomfortable, magnificent one. Nobody did this, and it was not mere chance either. It followed. It would be easy to feel that explaining the patterns this way drains the wonder out of them, that to say it followed from the laws is to make the cosmos ordinary. The very opposite is true. There is nothing ordinary about a universe whose rules hold so perfectly steady that a force as feeble as gravity can labor for 14 billion years and never once find them shifted beneath it, whose smallest atoms are stamped out identical across distances that light needs 10 billion years to cross, whose deepest regularities follow, by airtight mathematical necessity, from its deepest indifferences. An order that requires no designer and is yet not random is far more astonishing than either a tidy clockwork wound by some hand or a formless roar of chaos. We have not explained the wonder away. We have found out what it is made of, and what it is made of is more marvelous than the mystery was. Think of all that had to hold true for any of it. A single number, fixed in the first instant of the universe, the faintness of those original seeds, had to fall within a narrow window, small enough to grow slowly, large enough to grow at all. The strength of gravity, the identity of every atom, the constancy of the rules across 10 billion years of traveling light, all of it had to stay exactly itself, and it did. We live inside a consistency so deep and so dependable that we mistake it, every single day, for nothing at all, when it is in truth the rarest and most generative fact about our world. And we have come to ask these questions at a fortunate moment. The universe is old enough now to have built the stars, forged the elements, and assembled out of them minds that can wonder. And it is still young enough that the evidence remains legible. The afterglow of its birth still washing faintly across the sky, the stars still burning, the neighboring galaxies still close enough to read. Far enough into the future, all of that evidence will have dimmed and drifted out of reach. We happen to stand in the long-lit middle when the cosmos can be both lived in and understood. That too is a kind of fortune worth feeling. It is worth remembering, here at the end, how far the road has run. We began beneath an ordinary night sky, with the suspicion that its calm was only a surface. We followed the first watchers who staked their lives on the returning stars, saw the old wall between heaven and earth come down, found the same laws written into the light of distant suns, watched gravity, weakest of all the forces, gather the faintest seeds into galaxies and the cosmic web. Read those seeds with our own instruments in the oldest light there is. Trace the rules themselves down to the symmetries beneath them, and the conservation laws those symmetries compel. Saw the same few forms echo from the cosmos to the fern. Understood how order is bought on borrowed time, from a universe sliding into disorder, and arrived at the last, at ourselves. Stardust gathered into something that could make the whole journey and know that it had. It is a single unbroken thread, and it runs from a harvest calendar to the floor of physics without once being cut. And the marveling is not finished, because the deepest question of all still stands open. We trace the patterns down to the conservation laws, and the conservation laws down to the symmetries. And there, for now, the trail ends. Why the laws of the universe should be symmetric in the first place, why reality is built upon such constancy rather than upon none, we cannot yet say. It is the floor beneath which we have not learned to see. That unanswered question, and others like it, are what keep the work going, what draw each new generation back to the sky their ancestors first learned to trust. And there is something to carry away from all of this, standing exactly where you stand. You are not a spectator who wandered in to watch a cosmos unfold at a distance. You are a piece of that cosmos, assembled by the very same gathering that built the galaxies, running on the very same laws, arranged for a brief while into a shape that can understand the order it is made of. To grasp why the universe has patterns is, in the end, to learn something about what you yourself are, a knot of ancient, well-traveled matter, held in shape against the dark for a little while, reading the order it came from. If you have enjoyed this exploration of why the universe looks the way it does, a like or a subscribe helps us continue making them. And so, at the very end, look up once more. Go out on a clear night, away from the lights of the town, and find again that scatter of stars that can still, at the first careless glance, look like so much chaos flung at random across the dark. You know now what you are looking at. Not chaos and not ornament, but the visible surface of the deepest order there is. The same few unchanging laws, written everywhere at once, drawn out by gravity from the faintest of seeds, echoed at every scale from the atom to the web, and worked across 14 billion patient years into galaxies and stars, and the very stardust creature that now tilts its head back to take it all in. The night sky was never a mess. It was an answer, written across the dark in a hand that never wavers, waiting only for someone patient enough to learn how to read it. The Watchers began that reading thousands of years ago, staking their harvests on the returning stars. We have carried it a little further, down to the symmetries at the root of everything and back. And the reading is not done. The universe still has plenty left to reveal, and we will be following it as it does.